Hello folks, how's everybody doing? Another day, another lecture, another fireside chat. We have a reminder, 7th Rational Physics Conference coming up in 3 weeks. It's going to be in Bora, Sweden. Right now you're running against the clock. If you want to show up, well, better make your reservations. June 8, 2019, and that's going to be in the little town of Bora, Sweden. Okay, I'm going only because of the beer. There's going to be beer down there, and that's the only reason I'm going. So if you like to drink beer, you probably go to the right place. Anyways, what have we been doing for the last couple weeks? Well, we've been looking at space, the nature of space, wondering whether it's infinite or finite, wondering whether it's the same thing as the ether that we've had for now, I'd say at least 2,500 years, if not more, because this ether really comes from the 5 elements, and those came from the East as far as I'm concerned. It's very hard to track exactly who came up with all this, but it was known in the East, and somehow it got to the West, and everybody picked up on it. Oh, there's 5 elements. Someone must know. We got this from some kind of sage that knows more than me, so the guy says, I'll accept the ether. And we haven't let go of the ether. To this day, we have the ether. Mathematical physics doesn't like to recognize that, but yeah, we're dealing with the ether today. Ether simply means that space is made out of something. That's what ether means. And typically, people imagine it, most people, I guess, as a bunch of tiny particles there vibrating in the background. And they see that as space. They equate space with this ether, just a bunch of particles. Mathematical physics, especially quantum mechanics, the theory there, or the assumption there, it becomes theory in some cases because it just turns into an explanation. And that is that the assumption is that there's this vibrating whatever in there, particles, energy, fields, whatever's vibrating in there, and those vibrating whatevers are space. Same thing between space and this vibrating stuff, which, for lack of a better word, we can just continue with history and call it ether. Okay? Looks something like this. Here I have a little picture. And this is a finite ether. Okay? This is a finite ether. Not everybody will subscribe to this. Here we have the ether, which are those red little particles, and they have some kind of white background that encapsulates them. And then what encapsulates this whole thing is some black unidentified stuff. Okay? In this case, the ether is finite. And as you can see, within the cube, or the box there are 2 colors. There's 2 things. There's a red and there's a white. Okay, so if the red stuff is the ether, what is the white stuff? So that's the first question an ether proponent would have to answer. What is the white stuff? Okay, if we decide that they're both the same thing, well, we're going to end up with something like this. It's all the same thing, right? And so, you wouldn't have a difference between the little particles and the box. So the ether if you're going to talk about particles, you're going to say the red ones are particles, individual. Each one of them is a little particle. They have to be encapsulated, each one packaged separately. And whatever packages them, what are we going to call that? If we call it space, then we can say that ether is not space and space is not ether. Space is something else, in which case they would have to define what space is and what ether is, separately. And one of the things that people usually bring up when they talk about the ether is that they're infinite. that the ether is infinite. They even say that space is infinite. You know, these people have this idea that both space or the ether are infinite. And they would, if they're talking about waves, it would look something like that. All you have is waves in the background, okay? And this would be the ether, and the same thing is space. Even though, as you can see, if you can see each one of those lines, it's because something is contouring them. One line is different from another, therefore there's got to be a background, a backdrop to each one of these waves, whatever those waves are. So there is, again, when you have more than one color, more than one image, you have to identify both of them. If one is the ether, the other one, we'll call it space. You can't say that space is ether. Okay, but this would be what the infinite wavy ether would look like. Here you have a different version. This is the particle version. All these particles vibrating in the background. And again, as you can see, there's two colors there. There's a white and there's a black. If the little particles are the ether, okay, then what is the black stuff? And we have to say that black stuff is space. And so space is not the same thing as ether, and ether is not the same thing as space. In other words, space is not made of particles. The particles are what make the ether in this case, okay? Otherwise, you know, if you remove one of the two colors, we end up again with this nice, beautiful, uniform color. That's a single color. That's if space equals ether, right there. There's a more fundamental problem with the ether. And it's got to do with this, whether it's infinite. Aristotle, you know, he didn't believe in an actual infinity, okay? He didn't believe that there was an actual infinity. He said there's a potential infinity, you know, you can have numbers and so on, they can be infinite, and we can try to imagine that. But there's no real thing out there that's infinite. And he had a point, whether he knew it or not. I don't know if he really reasoned in the same way I'm going to reason it now. But the way it works in rational science, you define the word object. You have to define the word object in physics, because you can't do physics without objects. That's a fundamental principle. And so this is not ontology, this is not metaphysics, this is not philosophy of physics or of science. This is laying the foundations of physics. You can't do physics without an object. You don't need to define the word heart, because you're not going to be doing medicine. You don't need to know what a law or a regulation is, because you're not getting into a field of lawyering, of law. No, you're going to do physics. And so for physics, you've got to establish some foundations. And the foundation you have to establish is that you can't do physics without objects. And if that's the case, you have to define the word object. So this is a sine qua non type step, first step. You can't elude it. You can't say, well, yeah, we'll let the English majors define these words. We're going to do physics. No. You need to establish the foundations so that you can put the entire field of physics on solid foundations. And that is, you can't do physics without an object, and you need to define the word object. How do we define the word object for the purposes of rational physics? We say that an object is that which has shape. Very simple. It took 10,000 years for someone to come up with that definition. We've never had a definition of the word object. In fact, David Hume, 18th century, together with another 18th century fellow, Immanuel Kant, they thought that existence and object were synonyms, that there's no difference in saying that an object exists because all you're doing is repeating the word. You're saying that an object is an object, or exist is exist. They couldn't tell the difference between existence and an object. And existence is something else. We have a different definition for that, but I'm not going to bring it up right now because that's a can of worms, okay? Let's just say the word object needs to be defined. It's defined as that which has shape. All objects in the universe have a single property in common, and that is that they have shape. And if you know of any object that lacks this property, please get in touch with 1-800-SCREW-YOU, okay, and let me know, okay? Yeah, it's the only property that all objects have, okay? So an object has to have shape. That is what we're going to use in physics. All other criteria, see, touch, motion, volume, mass, are other issues that people raise. All those require a second object. You can't do, they're relations. And a relation is what a concept is. Concept is a word that requires two objects. So an object is that which has shape, and a concept is that which requires two objects. It's a relation between two objects. And so all these are concepts. None of them can be used to define the word object because it requires two objects in all cases, or two things treated as object. Motion, two locations of an object. It's like you're treating two things again. Okay, so all of them involve two. What an object is made of, which is pertinent to what I'm going to be talking about right now, that's also not a definition of an object. It's called mereology. And mereology is unscientific. It's kicked out of physics completely. And that is what an object is made of. In other words, we say, what is a table? And the guy says, well, it's made out of atoms. I don't care what it's made out of. In physics, we point to it so that the ET just came from another planet. He understands what the word table means. And you don't go in there and say, well, look, you know, a table is very complex because it's got all these atoms and all these molecules. And no, you point and you say table. That's it. You're done. He learned the word table. And that's how we do it in physics. You point to objects. You define concepts. Okay, so the question now is, ether an object or a concept? Is ether a standalone object that I can point to? Or is it not? How's that? Black or white? It is or it ain't. And if you say that ether is infinite, or that space is infinite, you immediately removed it from the list of things, of entities, of bodies, whatever word you want to use, somethings, things. They're not a thing. If it's infinite, it doesn't have shape. And only those things that have shape qualify as objects. In other words, the definition must be adhered to strictly. An object is that which has shape. Period. Very simple, very short, very concise, unbeatable. It's the universal property of all objects. If the ether is infinite, it's not an object. There is no object which has infinite shape. If I bring God tomorrow here and he talks to me personally, you know, my personal God, here's God all-knowing, all-powerful, he sits next to me. And he says, look, there's this object X. And I say, yeah, okay, what does it look like? And God says, I don't know. You know everything. You're omniscient. You don't know? What do you mean you don't know? Well, you see, Bill, this object is infinite. Infinite. What do you mean it's infinite? Yeah, it's an infinite object. But you should be able to stand outside and, you're all powerful, you're all omniscient, right? You can stand outside of the object, look at it from a bird's eye perspective and tell me what it looks like. Not so much, am I interested in what it looks like? No. I want to know if it has shape. That's a yes or no kind of question. You know, one thing is, what does something look like and does it have shape? Those are two different things, okay? And so does it have shape? And God says, well, it has shape, but that shape is infinite. No way. God fails if that's what he comes up with. He can't tell me there's an object by definition, that which has shape, and this is an infinite shape that he cannot imagine the shape, that he is not able to illustrate it for me, draw it for me. Okay, so we have a contradiction. There's no such thing as an infinite object. And the word infinite, in fact, is an irrational term. It should never be used, especially in physics or science. Adjectives in physics, for the purposes of physics, can only qualify, modify objects. Not nouns, not subjects, objects. The word motion in ordinary speech is a noun. And it can be the subject of a sentence. You can talk about motion. The motion of the earth. What is the subject of the sentence? Motion. You can talk about an orbit. You can talk about an itinerary, a trajectory. None of these words qualify as a standalone object for the purposes of physics. These words qualify as verbs. Orbit is a verb. Trajectory is a verb. Motion is a verb. For the purposes of physics. In ordinary speech, they're nouns. In physics, they are verbs. Okay? They're motion, they're actions. You know, you can talk about jumping, but jumping is is an action. It's not a standalone object. The kangaroo is what's an object, not his jumping. Okay? So let's keep that in mind. It's only objects which can be used as the subject of a sentence in physics, in formal physics. Only objects can perform motions. Okay? So if that's the case, you cannot say that motion is an object. Okay? So just the same nouns of ordinary speech do not translate, cannot be extrapolated indiscriminately into physics. Okay? So is ether infinite? Well, again, if ether is a physical object, it cannot be infinite because no object can be infinite. Okay? You cannot say a table is infinite. You should be able to see a table. You should be able to draw a table. You should be able to have an image of a table. If the table is infinite, how do you know it's a table? You don't see the edges, you don't see the borders because it's so big, or it's growing or whatever. So you cannot say that any object is infinite because it's a violation of the definition. And all objects are finite. And to say that, by definition, that which has shape. So you can't say there's an infinite finite. It's an oxymoron. And so you cannot say the ether is an object and that it's infinite. There is no infinite object. You should be able to draw a picture of ether if you claim that it's an object. And I don't care what you draw. I really don't care what you draw. You can say, look, draw a cube, draw a sphere, a circle if you want. I mean, I don't care, two-dimensional, I don't care. But you better be able to draw to illustrate your ether. And I don't care, you might say, well, it's made out of particles. We don't care what it's made out of. See, here you have a picture. Let's see if I can... Here you have a finite object. We'll call that the ether. And you say, okay, Bill, you smarty pants, fine. Here, I drew the ether for you. Are you happy now? And I say, okay, all I see is a bunch of particles, right, floating in space. And you call that body, that whole body is what you call ether. Ether is not each one of those individual particles. Those little balls there that are moving around, that's each one of those, that's not the ether. The ether is the entire shebang, okay? It's the whole thing. So I don't care if the ether is made out of particles and these particles are vibrating. This is what you have to answer. That's what you got to answer. There's your ether. Okay, that's the shape of the ether. And I don't care if that's the exact shape of the ether, that's irrelevant. The point here is that's if ether is presented as an object, it has shape. There you have a shape. Okay, so now we have a shape and we have some black stuff around that. And the question is, what's the black stuff? And I don't care if you use this one also. I mean, you can use this one and we've got the same question. What is the black stuff? The one inside and the one outside. What is the black stuff? And if you say, well, that's space, okay, then now you have to define what space is. Is space a physical object? Is space infinite? We get into the same question. You can't elude the question. no matter how you twist and turn it, you're going to have to settle this before you begin your theory. Okay? So this is the issue. The issue is that we work off of definitions, and a definition of an object is that which has shape. And if you're going to claim that the ether, space, whatever you put, space-time, you're saying that it's an object, you better be able to tell us what it looks like for the purposes of your theory. And if you encapsulate it, you say space-time is this, or space is that, or ether is that, we want to know what's outside of it. It's part of the definition, part of what you're going to need to illustrate it. If you can draw a line about it, I want to know what's on the other side of the fence. You can't allude and say, well, we don't know what's on the outside. We've never been there. This is not an issue of observation. It's not an issue of proof, of experiment. It's a conceptual issue, strictly conceptual. So you should be able to tell me what that stuff is outside there. In rational science, it's very simple. Objects, that which has shape. Space, that which doesn't have shape. Okay? So is space infinite? No, because there is no such thing as space. Space is a synonym of nothing, and nothing is that which doesn't have shape, which is the opposite of something, which is that which has shape. Now we can use these words consistently so that someone can follow our presentation. End of story there, okay? Okay, and well, what does mathematical physics do? Well, they introduce fields. Here's a field, okay? This is not a football field, okay? Nothing like that. Here's your field. Vibrating field, particles in quantum, and they had to kind of merge it with relativity, and they say, look, the little particle that's vibrating there, what it really is a field that's vibrating. Okay, so what is a field? What are those lines? And what is the black stuff in the background? What gives shape to each one of those lines and to the particle itself? You got to specify that. You can't say, well, I'm not going to talk about that background because we've never been there. We don't know what it is. No, you got to tell me what that black stuff is. I need to know what the black stuff is. That's the one I'm concerned about. And the other problem is, they have something like this. They say, look, it's got to be malleable. It's got to be flexible. Why? Well, because space-time, right? Because, and essentially this is more for space-time, but you could apply it to quantum mechanics as well. But why do you need this? Well, they need this because of this. You're going to have this, you're going to create a gravity well. The sun is going to weigh down space-time, so it's better be somewhat flexible so that the Earth falls, around the sun. That's the first one. And also you can see this as a black hole. If you got things going inside the black hole, the black hole's walls better be flexible, somewhat flexible. The other issue is that keep in mind that the sun doesn't stand still. The sun moves around, and according to the official version, it affects whatever happens on Earth after 8 minutes. That means that there's something traveling from the sun to the Earth, and that more or less has to be somewhat malleable also. Okay, so this is the flexible version of space-time. Now let me show you the rigid version of space-time. Here's the rigid version, okay? That's Mr. Blair. He's a so-called physicist. He's a mathematical physicist. And he says, I'll just read the last line, space is a billion, billion, billion times stiffer than steel. Okay? Yeah, that's what they say. And so here we have it. We have a tesseract. That's supposedly a four-dimensional. It's really what I see in front of me is a three-dimensional double cube onto a two-dimensional surface, or a platform or a background. And what they're trying to make you believe is that this is a four-dimensional object. Okay, fine, let's concede that. But it's got to be rigid because if you're going to send transverse waves like gravitational waves, you can only send those through rigid medium. If this were a gas, if this were a fluid, some kind of flexible medium, you couldn't send transverse waves, and then their theory of transverse waves, gravitational transverse waves, would go down the drain. So what they've done is they built both rigidity and flexibility. They built that both into their space-time. Which one are you supposed to accept? Which one are you going to use? Well, these mathematicians use this one, the other guys use that one, and everybody's happy. Nobody questions anything. Okay? Okay, why is all this important? Well, because as we were talking about last time, not only light is considered to be the vibration of the ether, but for a long time, in fact, people today even believe this. People believed and still believe that magnetism and electricity, they have something to do with this ether, with this stuff that we can't see. We can't see the air, we breathe it, but we say, those are atoms. All this air going in me, I'm just swallowing atoms. But when you talk about magnetism, light, and when you talk about electricity, well, they're not made out of atoms. So what are these things? And so they had to say, well, there's another something in there, and we'll call that the ether, for lack of a better word. Okay? And yeah, they would like to use words such as fields. And what is a field? Well, again, we have no definitions of these words, and that's why they like them. They say it's energy, it's fields, it's mass, it's charge. They use all these concepts, and they think they're talking about physical objects. They think they're talking about physics. They're not. They're talking about, they're doing philosophy. They're doing ontology there, if anything, Okay, so what happened? Well, we had to go back and look at two things. Not only did we look at light, because that was the vibration of the ether, we got it all the way to the 17th century, but we also had to look at magnetism and electricity, which I talked about the other day a little bit, and that started essentially, it took off in the 17th century. That's where it started, that's the moment it started, and then in the 18th century it took off much more stronger. And you take it back because you got to go all the way to the Greeks. Did they know about this stuff? And yeah, they did know about electricity. They probably saw lightning, which they said, well, that's Zeus throwing his spear or whatever, right? They didn't know what it was, but they didn't know that was the same stuff they got out of amber when they rubbed it, which was static electricity. They didn't know that those were the same things. Or, like I said the other day, the electric ray, which they were familiar with, they would step on it to cure their gout or whatever. Okay. They had all these encounters with electricity, but they never tied them together. They never researched them. They never investigated any of that. And that's not going to happen until much later. And it goes first through magnetism. Magnetism gets looked at first. First century BC, we got Mr. Lucretius, and he writes about magnetism. He writes, they found this poem in the 14th century in one of the churches. A miracle that they really got a hold of this one. And it's got 6 parts to it. And the last part, known as On the Nature of Things. The last part, Lucretius, I'll just summarize what he says because it's a little contorted. He's a poet, okay, a rich poet. Came from a very rich family, and he knew several languages, etc. He was well educated. And he was in line with Democritus. He was an atomist, okay? And he says the following, essentially. He says, he's trying to explain why the lodestone, the only magnet they were aware of, the lodestone, how it works, how it attracts. And he says, the lodestone discharges a flux of seeds, okay? The seeds sweep away the air between the lodestone and the iron. Okay, so we're talking about the space between the lodestone and the iron. And again, think of ether because that's what these people had in mind. They thought about particles of ether. He's saying the seeds sweep them away. The iron is sucked into this vacuum. Why? Because the iron moves as a result because it has tightly bound atoms on the one hand, and the air behind the iron also pushes it into the vacuum. Okay? So essentially, this is the first description of what is known today as the Casimir effect. You want to put two things together, you don't use pull, you use push. And the way you do it is you just remove whatever's keeping them apart. And you remove that air, whatever's in there, and whatever's on the outside pushes them together. That's the mechanism that Lucretius was proposing. And he also adds that air inside the iron also compels the iron to move. So he said there's this interstitial air. Okay, so we have this first description, this first attempt at explaining a magnet, which I think was quite interesting. You got two magnets, and he said, remove whatever's in between, and whatever's on the outside, push them together. So his idea was that the magnet was releasing some kind of seed, some kind of particles. He was an atomist. He was probably thinking of Democritus's or Leucippus' atoms just coming out of the magnet, pushing the air aside, and says that vacuum, now that draws them together. Okay, or at least the iron towards the magnet. Okay, we didn't stop there. A few hundred years later, about 400 or 500 years later, we have another nice description. You can see how slowly this went. We're talking about here difference, what I'm going to show you now, 500 years difference. Okay, did we make a lot of progress? Well, let's find out. This is St. Augustine of Hippo. Okay, he worked in Alexandria. Okay, he also went to Rome. Pretty interesting fellow. He wrote quite a bit on religion. He was a very religious fellow. And he says the following. He says about the magnet. Okay, and he talks about it in his magnus opus, his work known as City of God. Okay. And he says, I was thunderstruck, for I saw an iron ring attracted and suspended by the stone, talking about the lodestone. And then, as if it had communicated its own property to the iron, it attracted and had made it a substance like itself. In other words, it magnetized, right? This ring was put near another and lifted it up. And as the first ring clung to the magnet, so did the second ring to the first. A third and fourth were similarly added, so that there hung from the stone a kind of chain of rings, with their hoops connected, not interlinking, but attached together by their outer surface. So he was stunned by this, but he says, yep, far more astonishing is what I heard about this stone from my brother. And he told me that Bathanarius, right? He says, produced a magnet and held it under a silver plate on which he placed a bit of iron. Then as he moved his hand with the magnet underneath the plate, the iron upon the plate moved about accordingly. The intervening silver was not affected at all, but precisely as the magnet was moved backwards and forwards below it, no matter how quickly, so was the iron attracted above. So that's a pretty good description of what a magnet does, right? And St. Augustine puts it as something astonishing, this phenomenon where you put a magnet underneath a plate and it moves an iron that's separated from the magnet by this plate. And so that's the 5th century AD. And this is as much as we know about a magnet. Anywhere on Earth, in China, in India, in the West, this is as much as we knew. Okay, we had very little understanding. And I found another, which I liked a lot. This is another description from another bishop, right? Marbodus, Bishop of Rennes. And he says, for anyone who wants to know whether his spouse is unfaithful, let him position the lodestone under her head while she snores. Soon, if chaste, she seeks to embrace her husband, yet she is not awake. But any adulteress falls out of bed, as if pushed by hand, compelled by a sudden stench, which the lodestone emits as proof of her secret sin. So if you want to know if your wife, your girlfriend is faithful to you, now you know what to do. You put a couple magnets on her pillow. Thinking about it, I think I might try that with my wife. I'd like to test that theory. Anyways, I'm going to check my pillow too, just in case. See if she put some magnets under mine. Anyways, we get to, who is it, Mr. Peregrinus, 13th century. And 1269, to be more correct, he was in a battle, and he was writing on the side. It was he's writing this to a friend of his, and he's saying, look, here's what I've discovered about a magnet. He says, should you wish to see how a lone stone attracts another? And he goes on to explain how north attracts south and south attracts north, and south repels south and north repels north. So that's as much as he knew in those days. We covered that last week. So this is the progress we were making up to this point, okay? And so we reached the 16th century, the turn of the century into the 17th century, because it happens in the year 1600. And we get Mr. Gilbert, William Gilbert, and here he is doing his experiment in front of Elizabeth I. Okay, he worked with magnets. He did quite a bit of study on magnets, but he wasn't the originator of a lot of the ideas. He picked up a lot of ideas not only from Peregrinus, which he read. There was another guy also, Robert Norman, who discovered the declination of the Earth. And so he read these guys, and he had already some idea about magnets, but he decided to test some of these theories out. And one of the things that Gilbert does is he invents the forsorium, okay? The forsorium, I'm sorry, which is an electroscope. And he writes about it in 1600 in his book, De Magnetism. And in the Magnetic, he says, look, you can essentially make a compass, but not out of a magnetized thing. You can do it with electricity, or electric as he called it, electricus, the words he uses in Latin. And that word had been around already. He did not really invent that. And what it is he says, look, you put this piece of metal that looks like an arrow there, and you rub not a plastic, he did it with amber, and then you can move the thing around like a compass. So this is not a magnetic compass, it's an electric compass. That's what it is, essentially, electroscope. Okay, so how does he explain this? How do you explain this magic in his book? And he sets the precedent, which Audubon Garrigue is going to use later on. Garrigue reads Gilbert, okay? And he says, this is what he explains. He says, since no action can take place by means of matter unless by contact, these electrics are not seen to touch. But, as was necessary, something is sent from the one to the other, something which may touch closely and be the beginning of that incitement. He's saying there's something coming out of whatever has the static electricity, okay? And he goes on to show a picture. That picture comes from his book, okay? And it says, the one on the lower right there, it says, it is plain that the rod EF, okay, you can see EF there, the one on the left-hand side of that picture. He said, which floats on the water by reason of the cork, H, and only has its wet end F above the surface of the water, is attracted by the rod C. If the rod C is wet a little above the surface of the water, they are suddenly united, just as a drop adjoining a drop is attracted. So a wet thing on the surface of water seeks union with a wet thing, since the surface of the water is raised on both, and they immediately flow together just like drops or bubbles. But they are in much greater proximity than electrics, because remember, electrics was action at a distance, right? And are united by their clammy natures. If, however, the whole rod be dry above the water, it no longer attracts, but drives away the stick EF. So what Gilbert concluded from this analysis, that the electric, whatever was electric, the static electricity thingy that was coming out of a rod or whatever he used, was some effluvium, as he called it. It was some kind of vapor that he couldn't see, and he likened it to water, to some kind of humidity that was going out of the rod and attracting whatever was on the other side. He couldn't figure out the mechanism of attraction, but he says there's some liquid, some fluid, something coming out of this rod, and that's what produces the attraction. And he says all electrical attraction occurs through an intervening humor, keep in mind, humor comes from the Greeks. And they had this idea that all the liquids, all the fluids in the body, like saliva, semen, blood, all these were the humors. And they try to cure illnesses by attacking or addressing or somehow curing whatever fluids you had in your body. They thought that's the way to cure you. And so Gilbert picks up on this humor, and he thinks that's what's flowing out of one of these static electric rods. Okay, so it is by reason of humor that all things mutually come together. If that effluvium had been thick as that of air, then the effluvium would drive everything away, not allure it. But those rare effluvia take hold of bodies and embrace them as if with arms extended, with the electrics to which they are united. And they are drawn to the source, the effluvia increasing in strength with the proximity. In other words, he had realized also what Coulomb is going to discover some years later, and that's that there is not only an action at a distance, but that the closer they are, they attract with more force. Okay, he's already had this idea in there. We're talking about electrical attraction, charges, if you will. Okay. Okay, he does realize, even though Guericke says that he doesn't understand the difference between magnetism and electricity, maybe to some degree because his explanation is wrong, but I think Gilbert realized that there was a difference between a magnet and static electricity. And this is what he says. He says the difference between magnetics and electrics, obviously he's separating them, he's saying they're different phenomena, right? Is that all magnetics run together with mutual forces. Electrics only allure, okay? That which is allured is not changed by an implanted force, but that which has moved up to them voluntarily rests upon them by the law of matter. Bodies are borne towards electrics in a straight line towards the center of the electric. A lodestone draws a lodestone directly at the poles only, in other parts obliquely and transversely. Electrical motion is a motion of aggregation of matter. Magnetical motion is one of disposition and conformation. And this is maybe his only real contribution to magnetism as far as I'm concerned. The globe of the earth is aggregated and coheres by itself electrically. The globe of the earth is directed and turned magnetically. Gilbert essentially discovered that the earth was a magnet. And that's something we do owe to him. I can't say that he didn't contribute anything else. His book is quite interesting. It's quite lengthy, and he goes into a lot of detail of the experiments that he did. And the electrical part is relatively small because the only thing they knew about at that time was what Gilbert was breaking new ground on, and that's static electricity. He said, if you rub this amber, you can make this little needle move in the direction in which you want. And in other words, he made an electric compass. And that's about it. Magnet, he talks a lot more about magnetism, but again, he never figured out the mechanism of magnetism. In fact, to this day, Mr. Nobel Prize Richard Feynman, he has no clue. He couldn't explain, how a magnet attracts another, and he won't. I mean, none of these people will ever do so because they don't believe in explanations. They just believe in mathematics. They just want a description, but not an explanation of how Mother Nature does that mechanism, how she does her tricks, okay? Okay, shortly after, about 50 years later after Gilbert, we have Mr. Guericke, and I talked about him a little bit the other day. He took this sulfur, which was known to be electrostatically, it could be charged electrostatically, and he charges this ball. This is the modern version of it, okay? And with it, he is able to pick up very light things, okay? And he perfects these Guericke, right? He perfects these processes. He creates something that is able to rub the ball much faster. He can pedal it with his hands or with his feet. This one is a hand-pedaled one. And he is able to rub it at a higher frequency and create these effects where he attracts things with it. Okay. Okay, so that's more or less where we were at the other day. And what happens after that? Well, the British, they had created this group, the Royal Society, which was supported by the King, by the way, Charles II. And this was a think tank, okay? And these people, what they did, they thunk. They were supposed to come up with ideas, test things. They were the cutting edge of technology on the planet. Okay, so it's important to note that this was an important group of people for the times. Okay, there were groups in Amsterdam, especially in Amsterdam and Holland in general. There were groups in France, Italy, and Germany, right? But primarily, I think it was England that was at the forefront of all this, and they borrowed some ideas like from Gilbert, and they started using them. And among them, they took his vacuum experiments. Remember, Gilbert had evacuated the region within 2 hemispheres made of copper. He evacuated with a pump that he had, and then they couldn't break it open, so he created this vacuum. Okay, and he said, okay, this guy created the vacuum, we can do that as well. And they did that with a, you can call it I call it a bell jar because that's what it looks like. It's like a cylinder, a glass cylinder. They evacuated the inside of that, and they produced this vacuum, and they were able to control it much better than Gilbert did. And again, this is the Royal Society. And the guy who's going to work on this is this fellow here, Francis Hauksbee. And Hauksbee is the guy who's going to replace Robert Hooke. Robert Hooke was an enemy, a mortal enemy of Newton, of Isaac Newton. And as long as Robert Hooke was on the head of the Royal Society, which he was after the death of Robert Boyle, Newton was not even a member. When Robert Hooke dies, Isaac Newton takes over the Royal Society, and he names Francis Hauksbee. He names this fellow as his like a right-hand man. He's the guy who's going to do the presentations for him. He's going to do all the experiments, which was the job that Robert Hooke had in the old days, because Robert Hooke was a very manually oriented type of fellow, right? And Francis Hauksbee, he takes over that. And he creates this apparatus joining the two ideas, the vacuum on the one hand and the rubbing on the other. He creates this glass ball, okay? Evacuates it and rotates it. What he does in his lab, which was run by the Royal Society, what he does is he creates this. He creates a little plasma, okay? He creates the first plasma, really. Looks something like that. How does he do it? Well, he's going to go in there and, again, he's going to rotate this glass cylinder that we're going to see in a second here, glass bell jar. He rotates it, puts his hands upon it, okay? And he creates a static electricity, essentially, and with it, he ionizes whatever's in there, and that's going to create this blue light. And he's fascinated by that. He shows this to the other members of the Royal Society, right? And this is going to be at the beginning of the 18th century. I think this was in 1704 or thereabouts, maybe 1710, 1708, something like that. He's going to show this to the group, and this idea is going to take off in the 18th century. Is it going to take off in a scientific way? No, people started doing some other fancy things with it. One fella who is famous for it is this fella Stephen Gray, and he's going to create the flying boy. That's what the experiment was called. He takes a boy, he hangs him with silk threads because Stephen Gray had worked with silk. He realized that silk was not conductor, or not a very good conductor, and so he hangs the boy with these silk threads and has him tied to one of these machines, this rotating glass ball or glass cylinder, glass jar, and then he has the boy pick up light things with his hands, and he showed this experiment to several people. People liked were fascinated by the experiment. They thought this was so interesting for those days, that they could do these magical tricks. They didn't know how it was done, but they were fascinated by the magical trick, right? And so what happens? This idea gets spread around, and people start using it for different things. Here's another fellow. He's Gilbert, and what he does is he invents the electric kiss. He has a girl who is tied to one of these rotating glass jars, right? And she's isolated, and she's attached to it, and he has someone give her a kiss, and they both get shocked. And they're all fascinated by this experiment, the fact that you get this powerful smack because why? Because you you have this electric charge in you, which is released once you kiss the person who is grounded. In this case, the fellow who is standing on ground. He's making contact with the floor. Okay, and this fellow Georg also invents this little experiment, which is going to be taken over again by the British, a fellow named Benjamin Rackstraw, and he creates a museum with it. He has other experiments as well, but this was probably the most fascinating one. It's called the cherubification. And what it is they have this guy isolated. He's not isolated there, but he was in real life. And they charge him up, and through his head, he lights up the little halo that's on top of his head, this lamp he's got there, which is essentially a capacitor. He's got two plates separated by this region there, right? And he essentially is able to light it up. And people are fascinated by the fact that he does it simply by, they don't know how it's done, because Bose, the guy who came up with this, and later, I guess, Rackstraw did the same thing, and they didn't tell exactly how the secret was done. But what they were aware of is that they charged the guy, and the charge just went through the metal plate on his head onto that region and lit it up. And people were just fascinated by the effect. It was that's what people were using it at the beginning of the 18th century. They were using all these as tricks, as sideshows, as spectacles, and they would do all these tricks. Another trick was, the guy would charge himself up, and he would put cognac in a little glass cup or whatever, and he would light it up with his hands. They would do all these tricks, and people liked it. They were fascinated by it. Or they would charge himself up and then give you a shock, a static electric shock, touch you and do ground, So that's what electricity was used for in the beginning of the 18th century. But as we shall see, it's going to evolve, and during that century we're going to invent something very important, which is first the Leyden jar, and people didn't understand that very well, and some people got shocked in a very unpleasant way. But eventually they're going to come up with the famous capacitor. Okay, and that's going to be next time that I talk about this. The capacitor. That's going to be 18th century. And we'll see you, next Wednesday. And hopefully you keep in mind that we have the 7th Rational Physics Conference coming up the 8th of June. So if you're interested in going in Sweden, make your reservations. You'll see the information both in the my site there in Patreon, and you'll also see it on the Facebook site. If you look up 7th Rational Physics Conference, you should be able to find it. We'll see you on Wednesday. Bye-bye.